This is the expected value of directed panspermia. No worries. I'm a PhD candidate. I've been doing a PhD for the last 6 years, but that doesn't matter. So the concept of panspermia has been around for thousands of years, dates back to ancient Greece. It essentially describes the hypothesis that life on Earth originated from tiny seeds spread throughout the cosmos, and directed panspermia instead involves intelligent actors deliberately spreading seeds. And in recent years, it's been primarily discussed as something that we humans could ourselves attempt. Various methods have been proposed for attempting directed panspermia. So, for example, we could launch tiny pellets attached to solar sails containing freeze-dried bacterial spores inside of water-dissoluble UV protective sheaths, or we could hijack interstellar comets transiting through the solar system to convey microbial cargoes toward nearby planetary systems where they could disseminate the inoculum in their dust trails. These are just some examples. We note that our galaxy contains an estimated 300 million planets with conditions similar enough to Earth that they're suspected to be capable of sustaining life, and moreover, we could engineer bacteria to make them more adapted to the conditions present on exoplanets that we're targeting, in addition to being generally more resistant to the hostile conditions in space, which vastly increases the number of possible host planets for seeding purposes. So the key insight behind the concept of directed panspermia is that even if an individual chance of a spore surviving the flight, encountering a suitable planet, and successfully seeding it is minuscule, the overall probability of success can be made very large by dispersing vast numbers of spores across multiple payloads. And because bacteria are very simple organisms, it would be very cheap to attempt this relative to other spacefaring projects that we've been discussing today. But why should we attempt directed panspermia? What's the point? So in the paper, we describe two biocentric arguments, life-centered ethical arguments, which support attempting this project. I'll only focus on one of them, the strongest, in this presentation, which is to reduce the risk of life's permanent extinction. We know that mass extinctions are fairly common on a geologic timescale. Of these episodes, the worst, the Permo-Triassic extinction, is estimated to have wiped out over 90% of all marine species and about 70% of vertebrate families on land. This is the closest Earth has ever come to being completely sterilized. In the future, maybe we have the capacity to mitigate or prevent mass extinction events from occurring, but this is highly sensitive to the specific cause and severity of the event. In many other cases, it seems unlikely that humanity could do anything to reduce extinction risk, even assuming that we have greatly advanced technological capacities from the present. On the slide, you can see some estimates provided by Toby Ord. But on a long enough timescale, roughly less than 1 billion years, the sun is going to burn off all of the oxygen from our planet, and it will eventually engulf Earth as it becomes a red dwarf. So within our solar system, at least, life has an expiry date. So on the other side of the debate is welfarism, welfare-centered ethics, which we believe, or we argue, is opposed at the moment to directed panspermia because of its potential to create astronomical amounts of suffering in the long-term future. And this is not super obvious, so I'll just briefly explain why we should be concerned about this. So to a first approximation, natural ecosystems contain finite resources and evolutionary processes. Resource scarcity sets a natural limit on the consumption of resources within a given environment, beyond which the carrying capacity of that environment is exceeded, and not all individuals will have their energy needs met. And then evolutionary processes, on the other hand, pressure the inheritance of traits such that organisms are better adapted to navigate these limiting conditions in order ultimately to pass on their genetic information. It's just like patterns replicating through time. Because of these circumstances, there's significant diversity in the patterns of survival and reproduction that different organisms have evolved to follow, and these have variable effects on the average welfare of individuals. So a common strategy for animals such as mammals involves investing large amounts of energy into traits correlated with the survival of every individual offspring, which increases their chances of reaching sexual maturity and successfully reproducing. And the diagram here, this represents type 1 survivorship. But humans follow this strategy along with other large mammals such as elephants and whales. But these traits are typically quite costly, and each parent only has a finite amount of energy to invest into reproduction, so there's often a trade-off between survivability and fecundity, which is a term that's used to measure the quantity of offspring produced by an organism over the course of their life. Another viable strategy for having one's genes passed on involves optimizing for fecundity at the expense of survivability, as seen in type 2 and type 3 survivorship in this diagram. And this is vastly more common in nature, to the extent that we should consider type 1 strategists extreme outliers. It's a stable strategy only under very specific conditions. The problem with optimizing for fecundity is that for a population to remain stable over time, the number of deaths must be matched by the number of individuals who come into existence. So other things being equal, animals with higher levels of fecundity therefore have correspondingly higher rates of premature mortality. All animals reproduce in excess to their environment's carrying capacity. And for most animals, this ranges in the tens, hundreds, or thousands. Others, such as fish, range in the tens to hundreds of millions per parent. And while I lack the space in this presentation to assess the average welfare of such offspring members, elsewhere I and other philosophers have argued that it's plausibly negative, primarily due to the difficult circumstances they face throughout their short lives and the manner of their deaths. Evolutionary processes are not intrinsically concerned with optimizing for individual well-being, so we shouldn't expect that life in nature is worth living prima facie for any wild animal. And this is the primary question I've been researching over the course of the last 6 years as a part of my doctoral research. I'm happy to discuss it later on if anyone's interested. But for the time being, let's just assume that natural ecosystems might be negative in terms of their aggregated welfare, and if so, then welfareism opposes attempting directed panspermia because of the potential to create astronomical levels of suffering. So yeah, based on the arguments we've considered, there are strong biocentric reasons to attempt this. Strict proponents of welfareism are likely to oppose the project because of its potential to create astronomical suffering over the long-term future, and depending on how it's implemented, the consequences of attempting this could be permanent from the moment that we launch pansperms toward their intended destinations. For example, if they're micron-sized and traveling at 20 to 30% the speed of light, as has been proposed in the literature. There is therefore an asymmetry between these two positions. Attempting directed panspermia is equivalent to pulling the trigger on this particular suffering risk over billion-year timescales. A precautionary approach would thus favour waiting. We note that suffering risks are only a contingent byproduct of the seeding process, where natural selection is the sole force shaping biological evolution. But this outcome could be circumvented using future technologies and assuming that we have sufficient data to make predictions about what factors could promote welfare. So yeah, okay, cool. I'll just quickly skip by this. So it's possible, this is only contingent, the amount of astronomical suffering that this could cause. This could be changed if we had a better understanding of the dynamics of the problem. There is, of course, a cost to waiting if we take extinction risks seriously. See Nick Bostrom's astronomical waste argument. So basically, in the short term, we're proposing a moratorium on attempting directed panspermia, but we want more coordination toward creating technologies that could, if there was an imminent existential risk threat detected, do directed panspermia such that there's a functional alignment between biocentrists and welfareists. We think that it's possible to reconcile these two positions. We just haven't achieved the coordination. We don't have the right technology yet. So with that, I'll end. This is my website and my blog at the end. And yeah, any questions?
That was a lot of content for a few minutes. Okay, well, tons to digest here. Unfortunately, the presentation ran out of questioning time.
That's okay.
But thank you so much.